In this video, we'll introduce the core concepts and contributions of our work, knowledge-aware federated active learning with non-IID data. Federated learning allows decentralized clients to collaborate without sharing local data. However, the high annotation costs on local devices hinder its use. To address this, we integrate the principles of active learning into the federated learning framework. Active learning allows us to make the most out of a limited annotation budget by selectively sampling and annotating only the most informative data points. Federated active learning not only efficiently utilizes a limited annotation budget, but also prioritizes data privacy in decentralized learning. It ensures that sensitive local data remains secure while enabling collaborative model training. In federated active learning, we aim to attain a powerful global model on the server by sampling only local data and training the model on each local client. Each client maintains an active learning loop as shown in this illustration of the framework. A problem occurs when we need to improve the global model on the server but can only update client models locally via active sampling. We call this a mismatch between the active sampling goal of the global model and that of the local clients. The challenge is exacerbated when data is distributed non-IID across local clients. To better grasp this challenge, let's explore a scenario within our illustration. We can deduce that based on its local data distribution, client 1 might prefer to receive more labeled vehicle data. However, it turns out that client 2 already possesses a substantial amount of vehicle data. Providing additional labels of vehicle to client 1 may not yield significant benefits for the global model on the server. To deal with the mismatch problem, we propose knowledge-specialized active sampling. It intensifies specialized knowledge in local clients, ensuring the sample data is informative for both the local and global models. The formulation shows how we calculate knowledge-specialized KL divergence for an unlabeled data point X. Data points that yield a higher knowledge-specialized KL divergence are given priority during the sampling process. The underlying insight is rather straightforward. We aim for each client to select data from their respective areas of expertise, data they can confidently evaluate. To illustrate this concept, imagine a scenario where doctors are tasked with identifying informative medical images, while zoologists are responsible for pinpointing informative animal images. However, we don't require doctors to assess animal images, nor do we expect zoologists to review medical images. This selective approach ensures that experts focus their efforts where they can provide the most valuable insights with their specialized knowledge without venturing into unrelated fields. A numerical example on the right shows that our knowledge-specialized KL divergence differs from standard KL divergence. The active sampling priority of data points changes with and without the knowledge specialization strategy. To further deal with non-IID data, we introduce knowledge compensatory federated update. In scenarios where local data is both severely limited and unevenly labeled, clients may struggle, particularly with rare classes. Such statistical heterogeneity of clients can be harmful to the model aggregation process. To tackle this issue head-on, we've devised a compensation loss mechanism. It facilitates knowledge distillation from the global model to individual clients using unlabeled data. This process helps bridge the knowledge gaps on weak classes that clients may encounter. To validate and explore the effectiveness of our method, we conducted extensive experiments. The results from these experiments demonstrate the superiority of our method compared to existing state-of-the-art active learning baselines. Additionally, we've carried out a comprehensive component analysis, providing further evidence of the efficacy of our approach.